In this video, we are going to study the measure of spread known as the variance. Like in the case when we studied expected value or sample mean, sample average, we were implementing measure known as measure of central tendency, which is going to summarize our data set or information about PMF of our random variable x using a single number. Let's take a look at the following two distributions. So let's say we have first random variable here and second random variable over there. And the PMF of the first random variable given as follows. And the PMF of second random variable is given over there. So on the x-axis, I have the value of my random variable, and on the y-axis, I have PMF, probability mass function of that specific random variable. Now, let's assume that those two random variables have the same mean, the same expected value. Let's say it's defined somewhere over here. So expected value of x is equal to expected value of y. However, we can see that the second random variable y is its PMF is more spread out. So using a single measure of central tendency, expected value, we cannot compare those two random variables. By this reason, we have to implement a measure of spread, which is going to show us the dispersion of our random variable y, which is going to show us how spread our data is. First approach is to measure average of deviations of the values of that random variable from the mean. So we can calculate average of value of random variable minus its mean, which is the same equivalent as calculating expected value of x minus mu, where mu is expected value of random variable x. However, we can see that this value of expected value of that difference is always going to be equal to 0, since positive deviations from the mean are going to cancel out the negative ones exactly. So we know that expected value is a linear operator, so expected value of x minus mu is equal to 0. The second approach would be to take expected value of absolute value of that difference. And in some cases, we can work with this measure of spread here. Sometimes it is used. However, if we look from mathematical point of view, it's much more convenient to work with expected value of those square differences, since absolute value operator, we know that this function here is not differentiable, and it's much more convenient to work with expected value of square deviations from mathematical point of view. Which brings us to the following definition of measure of spread known as the variance. So variance of random variable in the case when we are working with discrete random variable is calculated as the sum of overall values of k, k minus mu squared multiplied by PMF of x. So expected value of those square deviations. In the case when we are working with continuous random variable, we need to calculate an integral from minus infinity to plus infinity, y minus mu squared multiplied by PDF of y, where mu is defined as expected value of random variable y. Now, Since we are working with the sums or with infinite integrals over here, we need those sums and integrals to be convergent for the value of variance to be defined. Then we require that expected value of random variable x squared and expected value of random variable y squared, those should be finite for the variances to be defined. Why we need exactly expected value of squared value for the random variable or expected value of squared continuous random variable to be finite will be clear in a moment. Also, let's take a look what is going to happen if we will work with expected value of squared deviations. Let's assume that the units of our random variable x are in meters. Now, if we calculate expected value of x minus mu squared, now the units of this will be in meters squared. So by that reason, if we want to keep the same units, we are going to implement a new measure known as standard deviation. So to deal with that problem, we can simply take a square root of variance, and this measure known as standard deviation, which is going to be in the same units as our original random variable. So notation for standard deviation is sigma, then variance is equal to sigma squared. Now, in most cases, rather than working with the original formula defined in this definition for variance here, we'll be using the following formula for variance, which is more convenient, which is more easy to calculate. Now, let's derive that formula. So variance of random variable omega is defined as expected value of omega squared minus expected value of omega squared, so minus mu squared. So mu is expected value of omega. Let's prove that for continuous case, and the proof for discrete case is relatively straightforward. So variance of random variable omega is defined as an integral from minus infinity to plus infinity of small omega minus mu squared multiplied by PDF of omega. So opening up the brackets here, we'll have an integral from minus infinity to plus infinity, omega squared minus 2 omega mu plus mu squared multiplied by f of omega d omega. Now, splitting up the following integral in the following way, we'll have integral from minus infinity to plus infinity of omega squared f of omega d omega minus 2. So mu is expected value of omega. I can factor it out of the integral sign from minus infinity to plus infinity. Omega f of omega d omega, and the last term is plus mu squared again can be factored out. An integral from minus infinity to plus infinity of f of omega d omega. Now let's take a closer look here. This integral here defines expected value of omega, so this is exactly mu. This integral over here is integral from minus infinity to plus infinity of PDF of omega, which is equal to 1. So all we are left with is an integral from minus infinity to plus infinity of omega squared f of omega d omega minus 2 mu squared plus mu squared. So this integral here then defines expected value of random variable omega squared. So this is expected value of omega squared minus mu squared. So mu squared is expected value of omega, which is mu squared, or it can be replaced with expected value of omega squared expected value of omega, right? Next useful property is given in the following theorem. If we recall, expected value operator was a linear operator. However, in a case when we are working with variance, variance is a quadratic operator. So let's prove that. So variance of A omega plus B is defined as, now using our newly obtained formula here, is equal to expected value of A omega plus B squared minus expected value of A omega plus B, so squared expectation of A omega plus B. Which is equal to, opening up the brackets here, we have expectation of A squared omega squared plus 2AB omega plus B squared minus let's use the linearity property of expectation operator. We'll have E, let's replace expected value of omega with mu for convenience, plus B squared, which is equal to A squared, expected value of omega squared, plus 2AB, expected value of omega, which is going to be replaced by mu, plus B squared, minus A squared, mu squared, minus 2AB mu, minus B squared. Those two are going to cancel out. Those two are going to cancel out too. So all we are left with A squared, factoring it out, expected value of omega squared minus mu squared, which is variance of omega. A squared variance of omega. So variance of A omega plus B is equal to A squared variance of omega. The concepts of measure of central tendency, expected value, and measure of spread variance that we have studied so far are just a special case of more general concept known as moments of random variable. Specifically, expected value is first moment of random variable about origin, and variance is second moment of random variable about its mean. The terminology suggests us the existence of other moments, higher moments, which are in some cases are used to measure different aspects of our random variable. For instance, measure known as skewness is going to show us how skewed our data is, and even higher moment, fourth moment of random variable about its mean is going to show us the shape of our distribution or the flatness of our distribution. We'll come back to that in a second. Let's start by looking at the following definition for higher moments of random variable. So omega is our random variable. R's moment of omega about origin is given by expected value of omega to the power of R. Now, obviously, we need to worry about the existence of our integrals or summations, provided that the following integral exists. The following integral is convergent. And in the case when we are working with discrete random variable, the similar summation sum should also exist, should be convergent. Now, R's moment of random variable omega about its mean is given by expected value of omega minus mu to the power of R. So if you recall the case when we were working with variance, variance is the second moment of random variable omega about its mean. Now, again, we need to worry about existence, provided that the following integral in the part A should also exist. Now, we have seen a first moment about origin, which is expected value, second moment about mean, which is variance. Now, third moment about mean is going to show us the skewness of our random variable. So if our data has a positive skew or its tail extends to the right, the PDF of random variable, similar PDF here, is known as positively skewed. So the value of so skewness, in practice, skewness is defined as expected value of x minus mu to the power of 3 divided by sigma to the power of 3, where sigma is the standard deviation. If the skewness value here is positive, then the PDF of that random variable looks something like this, where its tail extends to the right. In the case when this value is negative, it means that our data is negatively skewed and the tail of distribution extends to the left. And when skewness is equal to 0, it means that our data is symmetric as follows. So this is negatively skewed, and this is symmetric when skewness is equal to 0. Now, our next higher moment about origin is known as kurtosis. It is given as a fourth moment of random variable about its mean. In practice, kurtosis is equal to expected value of x minus mu to the power of 4 divided by sigma to the power of 4 minus 3. Now, in the case when kurtosis is positive, has a positive value, we'll have a lepta-Kurtic curve, which, as you can notice, has a higher peaked mean, and the tails are thinner, so thin tails. In the case when kurtosis is negative, we have a platy-Kurtic curve, meaning that it has a shallow mean and the tails are a bit fatter. In the case when kurtosis has a 0 value, we have a meso-Kurtic curve, meaning that it is moderate in breadth and curves, and it has averagely moderately peaked median. Now let's take a look at the following theorem about the existence of moments, of higher moments. If k's moments of random variable exists, then all moments of order less than k exist. By definition, k's moment of random variable exists. Let's assume that we are working with random variable x. If expected value of x to the power of k exists, or the following integral in the continuous case exists. So this integral should be convergent less than infinity. If this integral here exists, then it suggests us that all moments of order less than k also exist. So let's say we have other moment of that random variable I, which is, let's say, from 1 to k, strictly less than k. Then to show that all moments of order less than k exist, we need to show that all integrals from minus infinity to plus infinity of x to the power of I, where I is less than k, should also exist. So we need to show that this integral is less than infinity. To show that, let's start off by expressing that integral as an integral for the values of x less or equal than 1, xi f of x dx plus an integral for the values of x that are greater, absolute value of x that are greater than 1. F of x dx dy. Now, since the absolute value of x is less or equal than 1, the following sum of two integrals is less or equal than if absolute value of x is less or equal than 1, we can say that this term here is always going to be less or equal than 1. So the following sum of two integrals is less than if we replace this term by 1, f of x dx, f of x dx plus an integral for absolute values of x greater than 1, x to the power of I, f of x dx. Now, the sum from the integral from minus infinity to plus infinity over all values of x for PDF is equal to 1, meaning that this integral here is less or equal than 1. So we can replace it by 1. So the sum of the following two integrals is less or equal than 1 plus an integral for x greater than 1, x of y, f of x dx. Now, this integral over here is less than 1 plus an integral from minus infinity to plus infinity of x to the power of k f of x dx. Since yi is from 1 to k and the value of absolute value of x is greater than 1, this value is going to be less or equal than x, absolute value of x to the power of k, meaning that this integral is less or equal than this one. So the sum of 1 plus this integral is less or equal than this one. And this integral here is convergent. It is less than infinity, meaning that the sum of 1 plus this integral is also less than infinity, which was required to prove.